Hey everyone, how are you doing? Hope you had a good weekend and you're looking forward to the home stretch, last 2 weeks of school. I know there have been some questions about the grading policy that has come out. Please know that in the next day or two, you'll be hearing about how to communicate with that with your choice of P and X or regular letter grades. How you communicate that with me. So that'll be coming out here from all your teachers in the near future. So no need to send that in right now. I know some people have already emailed me, but we'll get that taken care of this week. This week also we've got a couple more Newton's laws to cover, and today we talk about something called momentum, which is a word you probably have heard of before. Another important physics concept. And hopefully by the end of the day, as you see for our learning target, we want to be able to calculate momentum and also understand something about called what we call the law of conservation of momentum. What happens when momentums interact and so forth. And we've got a little simulated lab that we'll be going through today. Well, what is momentum? If we look here, we've got momentum in this formula is the letter P, which is maybe a little odd, but M, as you see, is already being used for mass, and V is for velocity. The word momentum actually comes from the word impetus, which is in Latin has to do with an observed force. Okay, it is essentially a property. It is mass in motion. If you recall, we learned about Newton's first law, or the kind of the law of inertia, last week. Well, momentum kind of quantifies that idea of a body in motion wants to stay in motion. Um, but you'll notice not a body at rest, because if there's no velocity, there's no momentum. And so it strictly has to do with moving objects. Momentum is going to be measured in kind of a cumbersome unit a little bit, but we'll make it work. Kilogram meters per second is the unit that is used, and while it's a little bulky and awkward, it is very descriptive of what is measuring, because momentum, as we saw, was going to be the mass, which is going to be measured in kilograms, and the velocity, which was measured in meters per second. And so we just combine those units together to get the kilogram meters per second unit. All right, again, we've got that equation. Again, whenever we have one of those equations, we know that we can make that little triangle. We know that it can be more than one equation. It can be 3 in 1, essentially. We got momentum is equal to mass times velocity, but of course we can rewrite that some different ways. We can, if we want to find mass or velocity, we just have to rearrange our formula. You'll notice momentum's unit is kilogram meters per second again. The mass we'll do in kilograms. The velocity we'll do in meters per second. All right, in order to have a large momentum, okay, again, then, well, you want to have a large mass or a large velocity. Okay, those are the two factors that come into play here. Here I've got a truck that's got a 9,000 kilogram mass and moving 50 meters per second, compared to a moped that weighs 180 kilograms moving at 10 meters per second. Well, you can do the math. Obviously, the truck, because it's got much more mass and is moving much faster, has got a whole lot more momentum. Okay, so larger mass, more velocity, more momentum. A bullet is something that has a very small mass, but can have a lot of momentum due to its extremely high velocity. Quick little practice problem. We got a bowling ball rolling at a velocity of 15 meters per second with a momentum of 60 kilogram meters per second. What is its mass? Well, once again, we want to fill in what we know. We know the momentum is 60 kilogram meters per second. The mass is what we're looking for in this problem. If you read the question, velocity is 15 meters per second. So now I got to do my math. I set up my equation. P equals m times v. I know my P and I know my V. What I'm missing is m. So in order to get m by itself, I need to divide both sides by 15 meters per second, and lo and behold, I've got a 4 kilogram bowling ball. Well, what happens when the momentums of some different objects interact with each other? Well, that's what we're going to take a look at next.
All right, I've got two balls that both bounce pretty well. I've got a basketball and I've got a racquetball. And you'll see both of them bounce approximately the same height as just individually. When I put the racquetball on top of the basketball, however, and I drop them from about the same height, it's a big difference.
So in the video, we saw that both the basketball and the racquetball had momentum, and they interacted with each other in what we would call a collision of sorts. When a moving object hits another object, okay, some or all of the first object's momentum gets transferred to the other object. Okay, in the Newton's cradle experiment, a lot of you have seen that swinging ball hit others and it pops up on the other side. The first ball transfers its energy into the other ball, so it transfers its momentum. So the momentum before a collision is the same as the momentum right after the collision. This is what we call the law of conservation of momentum. You see the formula there, mv before is equal to mv after. Momentum is a vector, which means it has not just a magnitude, but also a direction. As a directional component. It's not just collisions here. You see these two girls pushing against each other. They're going to each develop some momentum in opposite directions, but because the momentum is going to be equal and opposite, the end result is the momentums cancel each other off. Okay, so momentum can be transferred from one object to another. Quick little math practice. Grandma's got a mass of 80 kilograms and a velocity of 6 meters per second before she runs into poor Sam with a mass of 40 kilograms and a velocity of 0. What's the final velocity of Grandma and Sam after the collision? Well, you see that Grandma's got a mass of 80 and moving 6 meters per second. Sam's got a mass of 40 and starting out at nothing, okay, in terms of velocity. So his momentum is 0 because anything times 0 is just going to be 0. When the two are combined, the mass is 120 kilograms as we add the masses of both Grandma and Sam together. The question is, well, what would the velocity be? Well, we can do our math, and we know that the momentum before the collision is the same as the momentum after. So if we look at the momentum of Grandma by herself, because Sam's momentum is 0, and then the combined mass of both of them, we got 480 kilogram meters per second for Grandma's momentum. We know the mass of Sam and Grandma combined is 120 kilograms. So the velocity, once I do my math and get v by itself by dividing by 120 kilograms, is going to be 4 meters per second. So she slows when she picks Sam up along the way. All right, quick little review. The video you see above here will be available to you on your notes. So we included that video. Very similar type one, what I did with the bouncing of the basketball. She's just a lot better looking. So when we got our formula here, okay, why does the racquetball bounce so high? Well, it has to do again with how that momentum gets transferred from one into another. Okay, and that the mass of the basketball is much greater than that of the racquetball, and so it has a lot more momentum, even though they're moving about the same speed. Well, some of that velocity then gets transferred into the racquetball, and so it takes off with a much greater bounce. Okay, momentum again is measured in kilogram meters per second. It's calculated by multiplying mass and velocity. We talked about that formula and the little triangle working the formulas. Again, what's needed to have a large momentum is going to be a large mass and high velocity. And during a collision, that momentum is conserved, the law, what we call the law of conservation of momentum. All right, so that's kind of where we were been trying to strive for. We're gonna do a little lab to try to pull this all together in this particular concept. And the lab is going to be done for you because we don't want to run into a deal where people don't have croquet balls and golf balls and so forth. But we're going to basically take a croquet ball and we're going to roll it down a short ramp and time it for how long it takes to cover 2 meters. Okay. Then we're going to set up the same scenario, except we're going to put a golf ball down at the bottom of the ramp. And we're going to run the croquet ball into that golf ball, and it's going to collide. And it's going to transfer some of its momentum into that golf ball. And so we'll time how long it takes the golf ball to travel the 2 meters. We'll also find the mass of the golf ball. Okay. Now the croquet ball, once it hits it, isn't going to stop. It's going to transfer some of its momentum, but it's going to keep going. So we have to time the croquet ball as well after that collision. And so what we're looking for essentially is to see how does the momentum compare of the croquet ball just by itself versus when there's that collision and the two run into each other. You're going to see on Schoology, on your quick quiz, a table that looks something like this. And where you see letters, A, B, C, D, E, F, G, and so forth, all the way up through J, those are blanks that are going to be filled in from the lab that we're going to demonstrate for you. All right, now it is going to be a matching section, so the numbers, you just have to find them and put them into the correct places. But they're of the video of the lab that we're going to do. So I'm going to kind of do the lab for you, and you just have to put the numbers in the right spot and do the calculations. So we'll roll that croquet ball down, let it run for 2 meters, and time it. We'll roll it down and hit a golf ball, time the golf ball for 2 meters. And then we'll roll it down, hit a golf ball, and time the croquet ball for 2 meters. And what we want to know is, will the sum of the momentums of the two after the impact equal the momentum of the croquet ball just by itself, that first run? Let's give it a shot. So fill in the data table that you find on Schoology and the quick quiz, and we'll see you tomorrow.